power series in a real variable x is defined as an infinite series with positive powers of x, right? So similarly, we have power series for a complex variable also, right? So I will write a more general power series summation a n z minus z naught to the power n, right? And n starts from 0 to infinity. So we have a series of the form, this form, and it can be written in expanded form also, that is a naught plus a1 z minus z naught plus a2 z minus z naught square and so on, right? You can see that it is containing positive powers of z minus z naught, and this series is said to is a power series and is said to be centered at z equal to z naught. This is called the center of the series, right? Because it is expanded in powers of z minus z naught, right? Is called a power series, right? Centered at z equal to z naught, right? And in particular, if I choose z naught equal to 0, right? If we choose that the center of this series is the origin, then this series will reduce to then summation a n z to the power n, n starts from 0 to infinity, right? Equal to a naught plus a1 z plus a2 z square and so on, right? So this series has center z equal to 0, means origin is the center of this power series, right? Then comes the convergence of this series. Convergence of a power series. So what do we mean by convergence? Actually, to understand the convergence behavior of a series, you need to know the convergence of a sequence, right? And then the sequence of partial sums. But for a student who has not studied much of the real calculus, he can understand this convergence in another way. I will try to write it one more way, and that is if you think of a binomial expansion of 1 minus x to the power minus 1, right? Consider in order to understand this convergence, right, from the another dimension, consider the binomial expansion of 1 minus x to the power minus 1, right? And you are familiar with this expansion. The expansion is 1 plus x square plus x cube plus, right? And it is an infinite series, right? X is a real variable, right? And this is obviously a geometric progression, and this is valid for mod x less than 1, right? Clearly this series is valid for modulus of x less than 1, and in that case it is called the interval of convergence. It means that when x lies between minus 1 and 1, you can write it as, that is minus 1 to 1, right? Means for any value of x lying between minus 1 and 1, right? And minus 1 to 1 is an open interval, right? So any real value lying between minus 1 and 1, this series is valid, right? For example, if you choose x equal to 0, that lies within this interval, and you put that x equal to 0 here on both sides, you will get 1 equal to 1, right? And not only for 0, for any number, if you choose x equal to 1 by 2 and put both sides, then these left hand side and right hand side will be equal, right? And if you put any number not belonging to this interval, suppose you put x equal to 2, which does not belong to this interval, and if you put x equal to 2 here, then it will give you 1 on the left hand side, right? 1 minus 2, that will minus 1 to the power minus 1, that will be minus 1, sorry, left hand side will be minus 1 for x equal to 2, and right hand side will be 1 plus 2 square plus 2 cube and so on, and that will be infinite, right? Means for any x which does not belong to this interval of convergence, right, this series is invalid, right? That's why we are calling it as interval of convergence. Means for any x belonging to this interval, this series is valid, right? And this is another way to understand the convergence behavior of a series, right? Okay, therefore mod x is less than 1 in this case is interval of convergence, right? And obviously we will call it an interval. This is a real variable x, right? And you are treating a real series in x, so that's why mod x less than 1 means x lying between the interval -1 and 1, all right? But since we are interested in power series in z, right, and one more thing is called power series, okay, and these a0, a1, a2 are complex coefficients, right? I should write it here. I will write that here, right, where a0, a1 dash 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 are complex numbers, right, and z is a complex number, z equal to x plus iota y, you know it very well, right? Fine. So we are interested in the convergence behavior of a power series in z, right, in complex power series. So similar to this, if I had 1 minus z here in place of x, we had 1 minus z to the power -1, then 1 plus z square plus z cube, right? And in that case, the series will be valid for mod z less than 1, right? And mod z less than 1 indicates a disk, open disk, right? Not an interval as in this case, right? There is a difference between mod x less than 1 and mod z less than 1. Mod z less than 1 indicates an open disk centered at 0 and radius equal to 1. Just remember the equation of the circle. That is mod of z minus a equal to small r. A is the center of that circle and r is the radius of that circle, right? So if you replace that equal sign, mod z minus a equal to, that replace that equal sign by less than, and then it will become a disk, right? So I will write in a similar fashion relating to this. Similarly, for a complex power series like this one, right, we have a disk of convergence, or should I write a region of convergence or domain of convergence? Domain of convergence, right? In place of interval of convergence, right, we are writing domain of convergence for a complex power series, and generally it is a which is a disk, right, of the form mod of z minus z naught for this series. So you can see that this center is z naught, right, less than small r, right? So this is an open disk, right, and we call it domain of convergence, and r is called the radius of convergence, right? Okay, and one more thing, this is an open disk. Do not put equal sign here because we don't know the convergence behavior on the boundary of the disk, right? Okay. Now, since we are dealing with the power series with complex z, right? So this will be our domain of convergence, and if you focus on this thing, right, then this will be the center of power series z naught, and this will be the radius of convergence, right? I will write it here, radius of convergence of power series given by this one, right? And this is center of convergence, center of series, or center of, right? Fine. And there are 2 or 3 facts about this power series, is that this power series always converge at its center, right? And if you see this power series, its center is z naught, right? And if you put z naught on both sides, it means that and this series will be valid for its center, right? And if you put z0 on both sides, you can see that the right hand side will be a0 because all these terms will go to 0, and the left hand side is also a0. However, it does not appear that it will give a0 because it appears that it will give 0, but remember that if you put n equal to 0 here, this will give you a0, right? The first term will be a0, and the second term will be a1 z minus z0 to the power 1 and so on, right? So the left hand side will eventually give a0, right? In order to see that the left hand side is giving a0, you should write this series in the form a0 is the first term, a0 plus summation running from n equal to 1 to infinity and an z minus z0 to the power n, right? Means the constant term should be written differently, right? And then you put z0 equal z equal to z0, then both sides will be equal to a0 equal to a0, right? It means that the power series always converges at its center, and that center is z0, right? And yeah, one more thing, the power series has a radius of convergence, okay, fine, and that is always a positive number, right? It may be 0 because sometimes the power series converges only at its center. In that case, this radius will be 0, right? If a power series converges for some points except at its center, means it is converging at its center, and for some more points, right, then the value of r will be positive, right? And it may be infinity. For an entire function, it may be infinity. We'll talk about that later, right? Okay. So we have a formula to find this radius of convergence, and I am writing those formula. A radius of convergence, right? So for a power series of this form, summation an z to the power n, right? I am taking the center at 0, right? N equal to 0 to infinity, that is fine. I am not writing that again and again. 1 over r equal to limit n tends to infinity an plus 1 over an modulus, right? So this r is the radius of convergence for this series, right? And we have one more formula, that is Cauchy's root formula, and that is actually limit n tends to infinity an mod 1 by n, right? So we can use two formulae to find the radius of convergence depending on the nature of this an, right? Generally we will use this formula, and if an is of the form something to the power n, means that like 2 to the power n, right, then we will use this formula. Both formula are absolutely fine. You can use them anywhere, right? So this r is called the radius of convergence, right? And one more thing, this is the domain of convergence. So a power series will always converge absolutely inside this domain of convergence, and outside this domain it will always diverge, right? Diverge means the left hand side is not equal to the right hand side, right? Okay. So taking numerical of this power series to find the radius of convergence, I will start with the simplest example. Example number 1, and let me find the radius of convergence of the following power series, right? The first is a part, right? The power series is summation z to the power n over n factorial, right? And n runs from 0 to infinity or 1 to infinity, that's fine. So you have to find the radius of convergence for this thing, right? So first you focus on what is your an. An is actually 1 over n factorial. The coefficient of z to the power n is an, right? And we'll use this formula, obviously. Solution. Here an equal to 1 over n factorial, right? Then 1 over r equal to limit n tends to infinity mod of an plus 1 over n, and if you write an plus 1 for this, that will be 1 over n plus 1 factorial and 1 over n factorial, right? and after cancellation it will give you 1 over n plus 1. You can see that n plus 1 factorial is n plus 1 times n factorial. That n factorial will cancel and you will be left with 1 over n plus 1, right? And if you approach n tends to infinity, it will give you 0, right? It means that 1 upon r is equal to 0, then r will be equal to infinity because it is reciprocal, right? So radius of convergence is infinite, right? It means that this power series has an infinite radius of convergence, and see the center of this series is z to the power n, means z minus 0 whole to the power n, means this series is centered at 0. It means that this function, the function representation for this series is an entire function, right? As we discussed in our last videos, that an entire function is analytic over the whole complex plane. It means that for if you are getting r is equal to infinity, infinite radius of convergence, it means that the function represented by this power series should be an entire function, right? And let us seek that function. What is that function? If you see this is obviously the power series of, I will write in detail, 1 plus z over 1 factorial plus z square over 2 factorial, right? You can expand it like this, and obviously this is formula for e to the power z, right? And e to the power z is an example of entire function, right? An entire function. That's why we are having radius is equal to infinite. Infinite radius of convergence directly imply the function corresponding to this power series should be an entire function, and that fact is supported by this example, right? Okay. Take another example. Summation 5 plus 4 eta to the power n z to the power n, right? So this is your a n this time. Solution here, a n equal to 5 plus 4 eta, right, to the power n. Fine. And since you see that this a n is obviously of the form something to the power n, I will prefer this formula, right, in order to this cancel this n, right? Okay. So using that formula, second formula, 1 over r equal to limit n tends to infinity mod of this 5 plus 4 eta to the power n, right? And that n will be cancelled with this 1 by n. You will be left with limit n tends to infinity modulus of 5 plus 4 eta, and that will be 25 plus 16, right? That will be 49, right? No, 41. Modulus of a complex number, that is x square plus y square, right? 5 is square plus 4 square is square root, right? So 25 plus 16, that will be a square root of 41, right? And therefore my r will be equal to 1 over square root of 41. So this is the radius of convergence. And if you are required to write the domain of convergence, I will write that domain of convergence, or should we say that the series converges for, right? Therefore series converges for, see this, the center is z minus 0, right? So z mod z less than 1 over root 41. This is called the domain. Roughly you can say that this is a domain of convergence, right? But you should write that series converges for this disk, right? Any number, any z belonging to this disk, right? And this is a disk centered at origin and radius equal to 1 over the square root of 41. So any complex number belonging to this disk, this series will converge, and by converge we mean this: the left hand side of the series is equal to the right hand side, right? Okay. Taking another example, see summation z to the power n over 2 to the power n plus 3, right? Okay. Solution, I am using this formula, right? 1 over r equal to limit n tends to infinity. We have a n plus 1 on the numerator part, and that will give me 1 over 2 to the power n plus 1 plus 3 over 1 over 2 to the power n plus 3, and this is inside modulus, right? And it will give me limit n tends to infinity 2 to the power n plus 3, and this is 2 to the power n plus 1 plus 3, right? And to evaluate this, you can take 2 to the power n common from the numerator and denominator both. I will be left with limit n tends to infinity 1 plus 3 by 2 to the power n, and here we will have 2 to the power n is taken common, 2 plus 3 by 2 to the power n, and then you approach n to infinity, that will give you 0, 0, 1 by 2, right, equal to 1 by 2. So therefore R will be 2, right? Okay. And similarly you can write the domain of convergence, that will be mod of z less than 2, right? Okay. D part summation, this time we will take summation a n z to the power n, where a n is given by 2 to the power n and 3 to the power n if n is even and if n is odd, right? So this time this a n is defined in this way. For even n, the value of the a n is 2 to the power n, and for odd n, the value of a n is 3 to the power n, right? So what we will do, we will find the radius of convergence for these cases if a n is equal to this one, right, and a n is equal to this one. We will have two radii of convergence, R1 and R2, right? Solution: for even n, if I treat n as an even number, that I will use this formula. Since 2 to the power n is here, right, so it will be good if you use this formula, because this n will be cancelled with this n, right? Okay. 1 over R1, I am calling it R1, right, equal to limit n tends to infinity 2 to the power n 1 by n, and that will give me 2, and ultimately R1 will be 1 by 2, right? For odd n, 1 over R2, applying the same formula, limit n tends to infinity 3 to the power n 1 by n, and that will produce 3, and this implies that R2 will be 1 by 3, right? So we have two radii of convergence for two subseries, right? I have taken as these two subseries of the given original series, right? So we see that the radius of convergence for the first series is 1 by 2, and this is 1 by 3, right? So which is the smaller of these two? This is small, this is 0.3 and this is 0.5. So out of R1 and R2, the minimum of R1 and R2 is this R2 1 by 3. So we can see that the radius of convergence for this original series will be 1 by 3, right? And why we take minimum, I will write that. Therefore R is equal to minimum of R1 comma R2, and that minimum is 1 by 3, right? The idea of choosing the minimum of these two numbers is that the first series, right, is converging within a disk of radius 1 by 2, or we should say 0.5, right? The first series is converging within a disk of radius 0.5, and the second series is converging for a disk of radius 0.3, right? And the original series was just the sum of these two series, right? And for the original series to converge, we have to take the minimum of these two, right? Means the intersection, a kind of intersection, right? Means any number that lies within the smallest of these two, 1 by 2 and 1 by 3, will definitely when put in this series, will give the left hand side is equal to right hand side, right? You have two series, one series and two series. One is converging for 0.5 and the other one is converging for 0.3, right? So the whole, their sum, the whole series will converge for their intersection, and their intersection will be their domain of their intersection domain will be mod z less than 1 by 3, right? Or you can write it here, its domain of convergence, you should write it as one even R1 is this, right? Therefore series converge for mod z less than 1 by 2, and similarly for this thing, therefore series converge for mod z less than 1 by 3. So you focus on these two domains or these two disks. This is a disk centered at origin, right, and radius 0.5, and this is the same disk centered at origin but radius 0.3, right. If I draw these two disks, the first one will be like this one, the first disk 0.5 radius, and the second disk will lie inside this first disk because the radius is less 0.3, so it will be like this, right. So any number, any complex number belonging to the inside of this smaller disk, right, this thing, right, the common part of these two disks will be a number which will produce a convergence series, right. Means any number belonging to this smaller disk, right, will give the domain of convergence finally, right, because if you choose number here like this number, right, if you take this point and this point, for this point the first series, this series will converge, but for this point the second series will diverge, right. See the domain of the second series, right. So we cannot say that series will converge for this region. Series will definitely converge for their intersection, and that is the inside of this smaller circle, right. Okay, or should I write it here? Series converges for 1 by 3 there. Therefore converges for mod z less than 1 by 3, and their intersection is taken, and this is their intersection, right. 1 by 3 and 1 by 2, minimum 1 by 3, right. Taking another example, E, and this time I will take summation 2 to the power n and z to the power 2n, right. So we can see that we have this z to the power 2n, right. Okay, so what can we do? There are two methods, either to convert this z square, right, you put this z square equal to w, right, and then it will go 2 to the power n w to the power n, right. Then you can use this formula, maybe the second one, right, and then at last we'll replace that w by z square, right. Or you can proceed like this way. If you have some number here 2n or 3n or kn, right, means this can be any number, right. So you should approach like this. You just use that formula, the second one, here 1 by r equal to limit n tends to infinity 2 to the power n 1 by n, second one, and we'll get 2 from here, right. Therefore r equal to 1 by 2, and but notice this is danger, this is not the radius of convergence, right, because this is not the series that is written here in this form z to the power n. So this is not declared as a radius of convergence, this is just a number, right, and in order to find the radius of convergence we should first write the domain of convergence, right. Therefore the series converges for, and you should notice this step, you just see this z is to the power 2n and you see this z to the power 2, right. So I will write mod z square less than this number 1 by 2, and you have to remove this square from here in order to get a disk, right. So square rooting both sides, you will get mod z less than 1 over square root of 2, right. So this is the final answer. So this will be the radius of convergence. This number is the radius of convergence, not this one, right. Therefore radius of convergence is 1 by root 2. Radius of convergence is 1 upon root 2, right. If we have had z to the power 5n here, right, so proceeding similarly, at this step we will be having mod z to the power 5 less than 1 by 2, and then mod z less than 1 by 2 to the power 1 by 5 will be the answer, right. Okay, taking another example, f. If summation a n z to the power n has radius of convergence r, find the radii of convergence of the first part is summation an z to the power 2n, right? And the second part is summation a n square, right? Z to the power n, right? This is the original series. It has a radius of convergence equal to capital R, and you have to find the radius of convergence for these two series, right? Okay. Solution. See the given power series, right? Clearly, if you focus on this thing, then 1 by R will be equal to limit n tends to infinity an plus 1 over an modulus. This is my equation number 1, and this is from this line. This has radius of convergence capital R, so directly implies this thing, right? Okay. Now focusing on first part, right? First part, let R1 be the radius of convergence of the first series, that is an z to the power 2n, right? Okay, then I shouldn't write it R1, right? Should I write it as for summation an z to the power 2n, right? Then 1 upon R1, let that number be R1, and don't say that this is the radius of convergence for this thing. No, because this 2 is still appearing here. Like this example, R is not the radius of convergence. The number appearing on the right hand side of this disk is the radius of convergence. So you cannot say that R1 is the radius of convergence for this, right? So be careful at this point. And now use that formula, limit n tends to infinity, and you can see that this is an, right? The same thing. Okay, so an plus 1 over an, the coefficient of your z to the power 2n. Okay, okay, now I can use this equation number 1 from here, right? And that value is actually equal to 1 by r, equal to 1 by r, using equation number 1, right? So you got r1 equal to r, right? Okay, then I will write the domain of convergence, or the series converges for what domain. Therefore, series converges for, you see the center of the series is 0, so I will write mod z whole square, because 2 is present here, right? And this number, and that is less than r1, and r1 is actually r, so that will give me mod z square less than r. Okay, that will imply mod z less than square root of r. It means that the number appearing on the right hand side of the domain of convergence will be the radius of convergence for this series. So this series has radius of convergence equal to capital R, square root of R, sorry, right? Therefore, square root of R is the radius of convergence for this series, right? And similarly, we'll find the radius of convergence for this second series. And before that, I have to rub the board. And for second part, I will write the series first, right? Z to the power n, right? So you should notice that this is not an, this is n square. So here, bn equal to an square. I am calling it bn, right? Okay. Then 1 over r2, and this time r2 will be the radius of convergence of this series. Why? Because this is z to the power n only, so we can say that r2 will be the this number will be the radius of convergence. Obviously, r2 will be limit n tends to infinity modulus of bn plus 1 over bn, and that will give you limit n tends to infinity. Bn plus 1 will be actually equal to an plus 1 square over an square, right? And that can be written limit n tends to infinity an plus 1 over an mod square, and using now again equation number 1, that is 1 by r, right? So it will become 1 by r square, right? So 1 upon r2 is equal to 1 over r square. So from here you will get r2 equal to r square, right? Now obviously this number r2 is the radius of convergence due to z to the power n, right? Therefore, radius of convergence is r square, right? Taking another example, fg, or I will change the question. Next question. Consider. I will consider power series this time, and let me take it to summation. Ak z minus 1 plus 2 iota to the power k. You can see that I have taken here ak. The coefficient is not known, but the center is known. This is written as z minus 1 plus 2 iota. You can take minus common from here, and you will get z minus 1 minus 2 iota. So the center of the series is known, and that is 1 minus 2 iota. However, the coefficient is not known, right? So consider this power series, right? Okay. Is it possible that this power series converge at some point? Let me take that point, any complex number. Let me take it minus 3 plus iota, right? Okay, minus 3 plus iota, and diverge at some another point, and let me take 5 minus 3 iota, diverge at 5 minus 3 iota, right? So you are given a power series, right, and that has absolutely some radius of convergence. However, you don't know what is the radius of convergence for this series. The only thing you know that the center of the series is 1 minus 2 iota, right? And you have to assume that the series converges at this point, and assuming that the series converges is at this point, you have to check or verify that the series diverges at this point, right? Is it possible, right? So the center of the series is given. Okay, solution. The center of power series is, you can see the center is 1 minus 3 iota. You should take minus common from here, and let me denote that center by z naught, 1 minus 2 iota. This is the center of the series, right? And okay, assuming that the series converges at this point, right? Yeah, assuming that the series converges at the given point, that is, let me call it z1 minus 3 plus iota, right? So I have assumed that the series converges at this point, and if the series converges at this point, then this point must lie within the domain of convergence, right? That is from the theory of power series. As I already said that a power series converges absolutely for any point belonging to its domain of convergence or inside it disk of convergence, right? And diverges for any point belonging to the outside of that disk, right? So in order to claim that this series converges at this point, right, I have to assume that this point will belong to the domain of convergence of this series, right? Or you can find the distance between these 2 points, right? This is the center of the series. Think like a disk, open disk, right? This is the center of the disk, right? And this is a point on the disk, right? And you find the distance between these two, right? That we'll call that distance d1, right? Obviously the radius of the disk will be greater than or equal to that d1, right? Means this point should lie within the disk, obviously, right? I will find the distance first. Then distance between z0, that is the center of the disk, and z1, right? That is d1, and the distance between two complex numbers is found by using this mod of z0 minus z1, the distance between any two complex numbers, right? Okay, so I will just subtract z1 from z0. You see from here that will give me 1 plus 3 4, and minus 2 iota minus iota, that will be minus 3 iota, and on doing modulus of this, that will be 16 plus 9, 25, and that is 5, right? It indicates that this Z1 point lies within distance of 5 units from the center, right? So the radius of disk can be greater than or equal to 5, right? Therefore, radius of convergence, right, can be greater than or equal to 5. You focus on this thing. Why I have written greater than or equal to 5? Because you know that at this point the series converges, right? And this point is at the distance of 5 units from the center of the series, right? So this point has to lie within the disk, right? So the radius of the disk may be greater than or equal to 5. It cannot be less than 5, right? Had it been less than 5, then this at this point the series cannot converge, right? Okay, so understand this relationship, why I have written greater than or equal to 5, right? Okay, and then taking another point, this point, right? Okay, now Z2 equal to minus 3 plus iota, this is the second point, and let me find the distance of this point from the center again, right? Okay, then distance between Z0 and Z2 is D2, and let me find the distance, that will be Z0 minus Z2, and let me see what will be D2. So this is Z0 1, that will be 3, and minus 2 iota minus 3 iota, I think, right? 1 minus 3, that will be 4. I think I have taken the wrong point. This is minus 5 minus 3 iota, sorry, 5 minus 3 iota, now it is correct. So 1 minus 5, that will be minus 4 obviously, and then minus 2 iota minus 3 iota, that will be minus 5 iota plus 3 iota plus iota, sorry, minus 2 iota plus 3 iota plus iota. In that case, it will be square root of 17, right? Okay, and you can see that this point, this distance is square root of 17, 4 point something, right, approximately. So this point is lying within this distance, within the domain of convergence, because the radius of convergence is greater than or equal to 5, and this point, the second point, has a distance of square root 17 from the center. It means that this Z2 point is lying within the domain of convergence due to its distance. And distance is less than the radius of convergence. You can see that, right? Root 17 is approximately equal to 4. It indicates that Z2 is lying within the domain of convergence. It means that this Z2, at this point Z2, the series will also converge, right? And but here in the question it is written that diverge at this point, so it is not possible, right? Which implies that Z2 equal to 5 minus 3 iota belong to the domain of convergence, right? Therefore, the series converges at Z2 equal to 5 minus 3 iota, right? So which is a contradiction to the assumption of the question, which says that it diverges at this point, but that is not possible, right? Therefore, the answer to this question is no, right? So this is it for power series, right? And in summary, I will say that the power series is generally of the form summation an multiplied by z to the power n, and you use two different formulae to find the radius of convergence. Radius of convergence is nothing but that is actually the part of domain of convergence, right? And if you know the domain of convergence, that is of the form mod of z minus z naught less than r, the right hand side number is actually the radius of convergence, right? And inside the domain of convergence, every power series converges absolutely, and outside the domain of convergence means outside the disk, the series diverges, right? But what happens on the boundary of the disk, right? On the boundary of the disk, a series may converges or at all points, or may converge at a single point or some points. Means anything can happen on the boundary of the disk. So we are not talking about at the point which lies on the boundary of the disk. You can see that I have made a less than symbol everywhere, less than symbol, right? Not an equal to symbol, right? Because that in that case that needs some special treatment at the boundary of the disk, right? And yeah, from here, which one? Yeah, if a series converges at some point which lies inside the disk, right, convergence disk, then at any other point which lies again the different point in the disk, the series must converge. It cannot happen that the disk is series is converging within a radius of 5 and there is some point which lies at a distance of 4 units from the center and then series diverges there. It is not possible. That point of divergence should lie outside the disk of convergence, right? So this is it for this video. Thanks.